Welcome to Calculus. Today we will investigate finding equations of lines tangent to trigonometric functions, focusing on using rules for differentiating trigonometric ratios. We'll take a look at two examples, one where we find an equation of a line tangent to the graph at a given point, and the second, finding equations of horizontal or zero slope tangent lines. Let's take a look at our first example. So this function is our cosine function. So we're looking at f of x equals cosine x. And my first task is to find the equation tangent to cosine of x at this given point, pi over 3 comma 1/2. So we're going to begin, as we do with all of these questions where we're trying to find the equation of a tangent line at a specific point. I want to find the slope of that tangent line. So to find the slope of the tangent line, I need to find the derivative of the function. Remember, that's how we had defined the derivative at the outset, was that it was representative of the slopes of all the tangent lines to the function. So we're going to differentiate f of x. And let's do that. So our function is f of x equals cosine x. So the differentiation of cosine x, which is f prime of x, is going to be negative sine of x. And there I'm just applying my differentiation rule for cosine. Well, at that point, I need to say, okay, at what x value? So in the point that I'm given, the x value is recorded as pi over 3. So I really want to find specifically what's the derivative of the f function at pi over 3 specifically. And that allows me to calculate this slope. So I'm really looking at negative sine of pi over 3. And so recall in unit circle, if I locate pi over 3, that's equivalent to 60 degrees. And that special right triangle has a height of square root 3 over 2, base half, radius 1. So if I'm thinking about sine, that's the vertical divided by the radius. So that's going to be square root of 3 over 2, but then I need the negative symbol since that's really just hanging out there in front of the sine. So that's the slope to my tangent line, is negative square root of 3 over 2. So at this point, I'm ready to start writing the point slope form of the tangent line. And remember, point slope in general is y minus y1 equals m times x minus x1. And there are three things that we fill in. We're looking at what's x1, what's y1, and what's the slope. So the x1 and the y1, those are defined based on my point. So my point I saw already, the x value is pi over 3. The y value is 1/2. And then the slope that we calculated from our derivative is negative square root 3 over 2. And that's my equation. All I need to do in order to be able to graph that is convert it to the slope-intercept form, mx plus b. So we'll distribute the slope through that x parentheses group. So it's y minus 1/2 equals negative square root 3 over 2 times x. And then I'm going to multiply negative square root 3 over 2 times negative pi over 3. And that's going to turn into a positive square root 3. I'll put the pi out front. So pi times square root of 3 over 2 times 3 is 6. My last step to solve for y here, get my mx plus b form, is to add half. Now I'm going to add that as 3 over 6 so that I have common denominators there between my two terms. And that will give us this tangent line equation, y equals negative square root 3 over 2x plus in my numerator pi square root 3 plus 3 over 6. And that's the equation of my tangent line. Now, a lot of irrational numbers there, again, because we're dealing with cosine, a trigonometric function. And we'll graph that in a moment. But what we want to do first for part B is graph the function itself. So we'll create our table. And for our x values, I'm just going to respond to what I'm seeing here on my coordinate plane. It's all in radians. So I'll put 0 and then negative pi over 2, negative pi, and then we'll go also positive pi over 2, positive pi. We just want to evaluate. So I'm going to start cosine negative x. So that's as if I had gone halfway around the unit circle and we're over on the left-hand side, but on the x-axis. So the cosine at that value, let me fix the screen, is going to be -1. We'll keep going. Cosine at negative pi over 2. Make sure I write pi in that first one instead of just x. Okay, cosine pi, negative pi over 2. So if I think about unit circle, that's going to place me at the negative y-axis. So negative pi over 2 is a quarter turn. And that's going to have a cosine value of 0 because there's no horizontal component to that y-axis. Back to cosine at 0. That's +1. So you can start to see a pattern. I think the next one should be 0. And that's confirmed. Cosine of positive pi over 2, that's now going in my positive direction. That's going to be 0. And lastly, cosine of pi, same as cosine negative pi, -1. So I can see that oscillation, that the y values go between -1 through 0 to +1 to 0 to -1 to 0 to +1. So I'll start graphing that function, then we'll fill in with a curve. So there's negative pi, -1, negative pi over 2, 0, 0, 1, pi over 2, 0, pi -1. And I can see that pattern now repeating across the points that I hadn't calculated the x values for. And then I'm going to fill that in with my cosine curve. Keep in mind, cosine, it's a graph that goes forever, bouncing back and forth. Oscillating is the math word, between -1 and +1. Now, if I try to locate my point here, pi over 3, 1/2, that would be right there. So right kind of to the right of the y-axis as it has its descent. So definitely if I think about the slope, -√3/2, that's a negative slope. In fact, I can just sketch this in. And definitely that tangent line, it's tangent to the curve at pi over 3, 1/2. It does intersect the curve in 2 places. So it's tangent at that point, secant as a line goes generally. In fact, most lines, in fact, all lines that would intersect cosine at least once would intersect at least twice, maybe more. All right, so that gives us a curve. What I'd like to do is just check that on Desmos. So I'm going to just quickly go to Desmos, and I just want to check to see, is that in fact a good tangent line? So I'm going to jump over to the graphing calculator, and I'll put in our original function, though. So that's f of x equals cosine x, and there's that curve. Here's our proposed tangent line at the point pi over 3, 1/2. So it's y equals, I'm going to just type it in exactly, -√3 over 2 x plus, and then I'll put my fraction pi times square root 3 plus 3 over 6. And I can see that that is intersecting right there. That's an approximation for pi over 3, 1.047, comma, half. If I were to zoom in a couple times, I could see that that really is an accurate tangent line. So again, if I find it there, I can see that that is a tangent line that very much intersects our curve in one point at pi over 3 comma half. So it does help to come back and look at Desmos just to confirm that the algebra is all in order. Well, let's take a look at our second example. So that was an example where we were looking to see what's the equation of a tangent line at a given point. Let's take a look at one where we have to find the horizontal tangent lines. So here I've got, that's my part A instructions. Find all points on the graph of f where the tangent line is horizontal. So my function here is secant of x. And what we need to remember is that if I'm looking for horizontal tangent lines, I'm really looking for where the derivative equals 0. So the derivative, I'll just notate that as f prime of x equals 0. And to think about that really is just to connect again the idea of derivative with the slope of the tangent line. The derivative is the slope of the tangent line. So if we're thinking horizontal tangent lines, those have a slope of 0. And that's the logical leap to say, when I'm looking for horizontal tangent lines, I'm looking to set the derivative equal to 0. So we don't need to linger very long. I just need to find the derivative of f of x. So from our work with derivatives of secant, we know that the derivative is secant x times tangent x. And immediately I'm going to set that equal to 0, and I want to solve. Now you may look at secant x tangent x equals 0 and just kind of scratch the head and say, where do I start? Let's remember that secant we could consider as 1 over cosine x. It's the inverse of cosine. Tangent is equivalent to sine of x over cosine of x. And when I look at my two numerators, so really I'm not focusing on the cosine denominators at all, I'm just looking at the 1 and the sine of x. I'm really thinking that the only way I could get a product of 0 there is for this sine of x to have the value of 0. Because if it were 0, 0 divided by anything is 0. Again, I don't really want cosine of x to be 0 because that would make an undefined situation. I don't want undefined, I want actually 0. So my mini equation that'll help me solve this larger equation is going to be simply sine of x equals 0. So we could do a couple things. We could use inverse sine, but really we just need to think, okay, on the unit circle, where are those angle values where sine is 0? So I'll sketch the unit circle. And remember, sine is y over r. So where I'm looking is really all the places where the y value itself is 0. So that's at 0. It's also over here at pi. And then it cycles around. So not just at 0 and pi, but if I went back to 0 but had gone a full circle, that's 2 pi. If I go back over to pi, that's 3 pi. And so forth, 4 pi. So basically what I can say is that x equals k, which is a constant, times pi, where k is a positive integer. We'll just limit it to the positive integers. And that would describe all the peaks on sine where we're seeing that value of 0. Well, let's actually calculate a few of these. So what I want to do is I want to pick up secant of x, and if I'm looking at different intervals of pi, it should give me the actual the y values. So I want to actually calculate a few of these here. So let's pick up our secant function. So let's just say what's f at, we'll go 0 to begin because that was our first one we had found. And then we'll also calculate f at, let's calculate f at pi. And just to see what happens, let's also calculate f at 2 pi. And again, this will tell me my y value. So f at 0, again, this is the original function. So secant of 0. And to help me calculate that, that's 1 over cosine of 0. Cosine at 0 is 1, so that's 1 over 1, or 1. So it looks like I've got some perfectly horizontal tangent lines going through the y-axis at 1. Let's write that, and its equation is going to be y equals 1. But let's see if we have any different horizontal tangent lines. So secant of pi is going to be 1 over cosine of pi, which is 1 over cosine of pi is negative 1. 1 divided by negative 1 is negative 1. So it looks like I also have a tangent line going through the y-axis at negative 1. And let's use 2 pi to see if there's any others, perhaps a third horizontal tangent line. Secant 2 pi is 1 over cosine 2 pi, which is 1 over 2 pi is equivalent to 0. So cosine at 0 is positive 1. And that's not anything different. Notice it's a repeat of my 1. And so what I'm seeing is that it's going to oscillate between having a 0 slope at negative 1, 0 slope at positive 1, negative 1, positive 1, back and forth and back and forth. So for part B, we've graphed the horizontal tangent lines. What we need to include now is where's the function? So let's finalize this question by making a small table for secant of x. And I'm going to use what's on the table to help me decide what x values to use. So 0, negative pi over 2, negative pi, positive pi over 2, positive pi. And here's our function. So it's secant of x. So we'll start secant of negative x, or negative pi, sorry, is going to be 1 over cosine negative pi, which is 1 over negative 1, which is negative 1. So we'll plot that point over here at negative pi, it's negative 1. Okay, let's turn our attention to negative pi over 2. So secant negative pi over 2 is going to be 1 over cosine negative pi over 2. Well, that's cosine at negative 90. At that place on the unit circle, cosine is 0. So that's going to simplify down to 1 divided by 0, which is undefined. Anytime we see that undefined in a trigonometric situation, it basically tells me there's a vertical asymptote. Okay, let's keep going so we can see these patterns kind of emerge. So secant at 0 is going to be 1 over cosine of 0, which is 1 over cosine of 0 is 1, which is 1. So then it bumps up here to 1. Let's see what secant of positive pi over 2 is. So that's going to be 1 over cosine of pi over 2. So that's the positive 90. But again, that has the value cosine at that 90 is 0 because there's no horizontal component. So not just 0, but 1 over 0, which again is undefined. So what we can see is a pattern forming. I've got an undefined place where there's a vertical asymptote every increment of pi, and I can place that all along the plane here, and then I've got oscillating back and forth, and I can confirm it here by calculating secant at pi. That's going to be 1 over cosine at positive pi, which confirms it. That's 1 over -1, which is -1. And then I can repeat that pattern. It's oscillating back and forth, but the difference between cosine and secant is that secant, its curve moves away from the x-axis instead of being bound down on the x-axis. And so we have these infinitely many, basically parabola-like curves that are bound on the left and the right by vertical asymptotes. And that really kind of illuminates, why do I have two different horizontal tangent lines? Well, one of them at +1 is for those upper curves. The one at -1 is for the lower curves. Well, thank you for joining for this second example, looking at tangent lines to trig functions. We've looked at writing tangent lines to trig functions at certain points. We've also looked at finding equations of horizontal tangent lines to trig functions. So I'll let you take a look at your own tangent lines. Thanks for joining. See you soon.